Welcome to another lesson with Teach All About It. Today I'm going to be looking at floating point numbers for A-level computer science. Okay, so let's have a look to start us off at the formula that you are going to use for floating point binary numbers. So floating point binary numbers, they are always calculated using 2's complement. Now that means that any part of a floating point number is going to be using a 2's complement representation in binary. Now if that isn't something that you are familiar with, I have left a link which will allow you to go back to our 2's complement lesson and make sure that you have covered that before you come here. So we're going to use an example of 10.75 for our example. Now what that means is that floating point binary not only allows us to represent a real number, but it allows us to represent a real number in the most efficient way possible. Now the formula that you can see on the screen, m times b to the power of e, what this means is m stands for our mantissa. The mantissa is the actual value that we are trying to represent. So where the mantissa can get larger or smaller depending on the number of bits that you can represent, that is going to affect the range. Now the times b to the power of e, the b in this particular formula means the base of the number, and because we are working in binary, that means that we are using a base of 2. So where you often see times 2 to the power of something, that simply means that we are using base 2. And finally, we have our exponent. So the exponent is there to show us how many places that we have moved our decimal place from its fixed point decimal representation in order to create a floating point binary number where our decimal point is always inferred at the beginning. Now that probably sounds absolutely horribly complicated until you see an example. So there are just 2 more things that I want you to make sure that you have in your notes. So first of all, we are working with a mantissa, which is the actual value, our base of 2, and an exponent, which means we are moving the decimal place back and forth. Now when we move a decimal place, if we move a decimal place to the left out of its fixed point representation, that means it is a positive number that the exponent will be, and if we move it to the right, the exponent will then be negative. So now I've given you loads and loads of complicated information, I'm going to show you what this actually looks like, and that all of this really, once you put it into an example, isn't as scary as you think it might be. Let's put our 10.75 into a floating point representation, and I'm going to put it into its smallest possible representation. So this is just one version of the type of question you might be asked in the exam. So here we've got, I'm going to put a minus 16, so you can't represent a 10 without a minus 16, because remember it's in 2's complement, so we are going to need to have a 0 here, 1010 for our 10, and then a 0.75 is a half and a quarter. If I simply put 1010, that would actually infer that that is minus 8. So it's really important that you remember that anything that you are representing is in 2's complement. Now what we then want to do is we want to take that decimal place and we want to bounce it all the way to the left so that it is in between our 2's complement minus, so that the most significant bit there, and the 1. So a positive number will always start with a 0, 1. If it's a negative number, it will start with a 1, 0. This is called normalization when we talk about it in floating point binary. So you can see there, I have drawn a wiggly line. Now in your exam, your examiner is going to be looking for that wiggly line because it's actually showing them that you understand that you are bouncing that decimal point from where it is in its fixed position over between the 0 and the 1. And the way that we then represent that using the formula is to write this out as 0.1 101011, and then this is your times b to the power of e times 2 to the power of 4. So there is your base, and you can see here I've written the exponent as a denary number. Now what that's doing is it's showing I've moved this 4 places to the left. And the next representation that I'm going to show, so this is the working that we want to see as an examiner, is here. So whether this is your teacher, whether this is an examiner, whether this is a mock, a real thing, this version of your working is going to show every single step of the process. So here we've got the same number, 0.101011 times 2, and then to the power of the exponent. Now we move this 4 places, and in 2's complement, the smallest number of bits that we can use to represent a 4 is 4, because we need a 0 for our -8 and then 100 for the positive of the 4. Now when you then put this out into an answer, you actually write out the mantissa without the decimal place. And the reason we don't need the decimal point anymore is because our exponent is telling us where to put it back. So we can infer that it is always between the 0 and the 1 if it's a positive number, and the 1 and a 0 if it is a negative number, and the exponent is then telling us where we put that decimal place back. So we're going to have a look here at an example, and this is a real life exam example. It's a little older than I would usually use, but this is a really good example, and ultimately these things don't really change. So we're going to have a quick look at this particular question in a bit more depth before we start answering. So in this exam question, we have been asked for a floating point representation, and they have specifically told us they want us to have 10 bits for the mantissa and then 6 bits for our exponent. Now that's really important, because if we then don't use 10 bits for our mantissa, it's going to really mess up how we represent our number. The fact that they've told us that 2's complement is used for both of them, that's lovely. They won't normally do that. They will assume that you know this now. So in this case, what we are going to do is we're going to calculate a floating point representation of the positive version, so a positive 192.5, so 192.5, using 10 bits for a mantissa and 6 bits for the exponent. So what we're going to do to start off with is we are going to write out our table. So in this case, I can't actually create 192 just using 8 bits. So I need to have my minus number as -256. Otherwise, I can't get the positive representation of 192. So I'm going to start off with the 192. Now, if you do need to check that, you can always just use a little bit of working space over there. Double checking my working, 128 plus 64, that is indeed 192. There is nothing wrong with doing this in your exam. If you need extra paper, there's always extra paper at the back of your exam paper, or you can ask for more. Once we have written out the integer part in its fixed point notation, then we add the decimal part, and again you can see this is still in its fixed point representation, and that's really important. You must start with a fixed point number. So now I've got this as a 2's complement fixed point number. I'm going to draw my wiggly line, and I would love it to see everybody drawing that wiggly line in their exam. So in this case, I'm going to bounce that all the way to the left in between the 0 and the 1. Now that bouncy line is also going to show you how many places you've moved it. It's also going to show really clearly to your teacher, to your examiner, that you understand how many places that you have bounced. In this case, we can now draw this out, putting the decimal place in the correct location between the 0 and the 1 because it's a positive number. We're going to use our m times b to the power of e, so there is the mantissa, there's that long binary number, times 2 because that's the base, to the power of 8. Our exponent is 8 because we've gone 8 places to the left. we're now going to take that positive 8 and we're going to show this as a 6-bit binary number in 2's complement. That sounds really complex, but all it is a positive number of 8, making sure that you are using 6 bits. So instead of the 4 bits that you would have for a standard 8, you're going to put 2 zeros before it, and that's going to be a 2's complement version of a positive 8. Now once you've got to this stage, you are then going to make sure that you are placing both of your mantissa and your exponent as an answer clearly within either the answer space or if there isn't an answer space at the bottom. So in this case they've given us a really clear answer space for both of them, but if you don't have that at the bottom where they would give you extra space, then make sure you put M equals and E equals. Okay, so that would be a standard example of converting a denary number into a floating point number. So we're going to finish with a slightly more complex example from OCR. And in this case, what they've done is they have given us 3 floating point numbers. And you can see here they are, there's A, B, and C. And then they've asked us to add these together and then show the answer back in the same representation as they've shown here. So you can see here we've got 6 bits for the mantissa, 4 bits for the exponent, both using 2's complement. And again, what we're going to have to do is we're going to have to add these together. We are then going to have to return it to a 6-bit mantissa and a 4-bit exponent. And I'm going to show you how we're going to break this down. So the first thing we are going to do is I've labelled them A, B, and C just for making my life a little easier. Future me will definitely thank me when I'm answering this particular question. I'm going to calculate each one of them. I'm going to put it into a fixed point number. And that's really important in order to do the addition. So we're going to turn each one into a fixed point number. So A, we're going to put that into its representation. So we know that we've got our number here with its in 3rd decimal place to the power of 0010. I'm going to convert that exponent now into a denary number, and I'm going to bounce that in 3rd decimal place between the 0 and the 1 back into its fixed point location, and that is going to give me my fixed point representation for number A. I'm going to do the same with B. So in this case we have a similar number, we have a different exponent, and we put it in the same representation. And again, we can now put that in as a denary number and use our very, very short bouncy line to move it by 1 place. And you can see here, as I am going from a floating point into a fixed point, which is going in the reverse of what we just saw in the last example, instead of going left, I'm going right because it is a positive number and I'm putting it back. So everything happens in reverse when you're going from floating to a fixed point. So for B, that means we end up with 01.1, and then we'll put those zeros in there as well. And C, in exactly the same way, I'm going to represent this using the standard way. And you can see here that this uses the same pattern. So although they will give us some marks for these, you'll probably get less for B and C because you're following the same pattern. But we're going to show our working all the way through. So now I've got my bouncy line. Here is my fixed point representation for all of those numbers, and I've done the first section of this question. So now everything is in its fixed point notation. Now I can put them together and use them for binary addition. And I do that by lining up the decimal points. So if I had left my decimal points where they were, you can see there 2 of them would be in the right place, but actually one of them isn't, because it's actually the exponent's only moving it by 1. So we need the decimal points in the correct place in its fixed point notation. So we're going to take those numbers, line up the decimal place. You can see there that's the decimal point is in the right place, but the zeros aren't quite Right, so what we're going to do is we're going to infill with zeros. Now the only place where you would add a 1 is on that third one. And actually we don't need to do it in this one because the third one is actually a negative number. And we know that it's a negative number because the floating point representation started with 1 0, not 0 1. So we are now adding together our numbers. So we can now add our fixed point numbers, making sure that we show that's really clearly what we're doing. And we can just put those additions together. I'm going to show that, yes, this is overflow. That's quite important as we add them together. Something to remember at this stage is that if you do the addition in binary, you get the marks. If you did the addition in denary, so say you worked out what they were and you then just use denary to add them together and then you put it back into binary, you get 0 marks for that. I am going to just double check that these are correct, and what I would normally do is to probably just sort of do this on the back on the scrap paper and then make sure I cross it out, because this is not how I have put these together. This is just checking. If you want to make it even clearer, you can just put confirming answer. They can tell that you've done the binary addition because up here you can see we have got our carries of our ones and we've shown our overflow. But what we've done is we've added 2.5, 1.5 and then minus 4.25. If we add those together, that's adding 2.5, 1.5 and then minus 4.25. We should get 0.25, which is what we do get if we get rid of the overflow. That's why we get rid of our overflow when we add, because otherwise we end up with something very, very strange, particularly with a minus number. So we've added together, we've got our fixed point, but we're not in the correct format yet. So in order to get to the next part, we then need to put this back into its other representation. 0.25 is a positive number. So our decimal point needs to go in between 0 and 1. Those should be our first two numbers. So the way that we then put this into a mantissa is that we put 0, 1 and then fill in with the rest of our zeros. So we only had 2 zeros after the 1, but because we can assume that a floating point number has an infinite number of zeros going off into the distance, that's what we can put there, times 2 and then to the power of 1. Now our exponent is minus 1 because we have moved to the right, not the left. If we move to the left, it would have been 1. If we move to the right, minus 1. Now again, we're going to represent that minus 1 using 2's complement. Now a 2's complement minus 1 has to be in its 4-bit exponent. So it has to be 4 bits. So we can represent that standard mantissa as we had before, times 2 to the power of 1, 1, 1, 1. That is 1, 2, and 4, so 7. And then a minus 8 because it's 2's complement, that gives us minus 1. So the final part of this is to then show very clearly that we have a mantissa. And again, you don't need the decimal point for this because it's now inferred. And then we have our exponent of where we put our decimal point. So where do we put that decimal point back in order to get us back to the original number? So answers like this are really complicated and you're going to be given marks for all of the different elements. So you get marks for showing the fixed point representation, you get marks for showing your binary addition, and then you also get marks for showing that conversion back into a floating point normalized number. So when you are showing your answers, try and lay them out in a way that you can show here is step 1, here was step 2, here was step 3. And this actually also gives you the reason for using 2's complement as a way of representing negative numbers, because if you were to use, say, sign of magnitude, this would be incredibly difficult. So 2's complement allows us to perform calculations much more simply and much more easily, even if it might not feel like it the first few times. So try and give yourself some examples like this one and the one that we saw before, and give yourself some random mantisses and exponents, and see if you can then convert them between fixed and floating point, add them together, convert them back and forth.